Hello again. So for today, we are going to be talking about a couple of theorems and how they're going to apply to some problems. The first theorem we're going to be looking at is the intermediate value theorem. The intermediate value theorem, I'm going to explain it by showing a graph. Okay, so imagine that you have 2 points, one at x equals a and one at x equals b. And the 2 points have to have different y coordinates. Therefore, f of a is a different value than f of b. Okay, and importantly, the graph of our function is continuous. So let's think about what continuity means. And I mean continuous for every value between a and b. So if a function is continuous, that means you can draw through it without ever lifting your pen off the paper. In other words, it's a smooth, unbroken line. Okay, so here's what the intermediate value theorem says, is that if you choose any value between f of a and f of b, let's call that value L, then our function f of x must equal L for some value of x between a and b, because the function has to be smooth and continuous. Therefore, it has to cross that horizontal line somewhere. And that place must be between A and B. Okay? Maybe let's call this point C. Okay, so to state this more formally, we must have f of x is a continuous function on the closed interval a to b, and f of a is not equal to f of b. So let me put, if this is true and this is true, then for any L in between f of a and f of b, there exists some C where C is between A and B, such that f of C equals L. Okay, so as you see, the formal statement of the theorem is very long, but if you just think about it graphically, it makes perfect sense. If your function is an unbroken line, it has to cross any value that's in between the two endpoints. Okay, so that's the intermediate value theorem. Now, one thing to note is that if f of a and f of b were equal to each other, then you might not necessarily be able to find a value of f of c that equals L, because if the 2 points f of b and f of a are the same value, then that doesn't necessarily mean that there's a value of L that's in between f of a and f of b. F of a and f of b, if they're equal, L, I guess, would have to also equal f of b and f of a. And then, you see, there might be a graph like that, so that our function is never equal to L somewhere between a and b, only at the two endpoints. Okay, anyway, so that's the intermediate value theorem. The next theorem that I want to talk about is the mean value theorem. The mean value theorem, in its explanation, is going to involve the theorem that we're talking about, the intermediate value theorem. That's why I wanted to talk about that first. And actually, the mean value theorem has a special case that is easier to talk about called Rolle's theorem. So I think we should start with Rolle's theorem and then expand it to become the full mean value theorem. Okay, so here's Rolle's theorem. Okay, so for Rolle's theorem, you need to imagine that you have a function that is continuous, and the two endpoints have the same height. And also, imagine that our function is differentiable between a and b. That means that the derivative exists for all values between a and b. Then, there has to be some place between a and b such that the slope is equal to 0. See, in that case, that would be that point right there. You see, if I tried to, draw a graph like going down first, I eventually have to go up, and there has to be a point where the slope is 0. See, this uses the intermediate value theorem if you were to consider the graph of the derivative of this function. You see here, the derivative starts off negative, but eventually has to become a positive slope. So somewhere in between, we have to have a slope of 0 by the intermediate value theorem. Now, the intermediate value theorem states that our function has to be continuous. So how can I guarantee that the derivative is continuous? Well, that gets into like the fact that, yeah, it's a little complicated. Let's not worry about that then. Okay, so let me formally state the Rolle's theorem as a statement. Okay, so that's going to be A and that's going to be B. So if f of x is continuous on the closed interval a to b and differentiable on the open interval a to b. Closed intervals mean you include the endpoint. Open intervals mean you don't include the endpoint. Okay, so we need to have these two conditions for Rolle's theorem. Then the derivative f of x is equal to 0 for some x in the interval a to b. Let me just state it like that. Now, some textbooks, instead of writing an x here, they'll say the derivative at c equals 0 for some c between a and b. Yeah, maybe I should write it that way with the letter c, because that's the way most textbooks explain it. So like in this graph, this would be the value of c, where the slope is 0 at that point. Okay, so this is Rolle's theorem. Let's do an example of applying Rolle's theorem to some problem. Okay, so let's say that our function is f of x equals x squared minus 3x. And note that f of 0 is equal to 0, and that f of 3 is also equal to 0. Okay, so we're going to sort of apply Rolle's theorem to prove that there must be some value between 0 and 3 where the derivative of this function is equal to 0. Now, Rolle's theorem is just going to tell us that, but let's also go ahead and find it to sort of show that Rolle's theorem is working. Okay, so first let me just explain why Rolle's theorem works for this problem. Polynomials, when you take the derivative, you wind up with another polynomial. We know polynomials are continuous everywhere. Therefore, the function's continuous from 0 to 3, and the derivative is another polynomial, and that's going to be, it'll exist everywhere. Therefore, the derivative exists for all values between a and b as well. Okay, so Rolle's theorem is going to apply. Oh, and our two endpoints have the same value. That's another thing that we need to pay attention to. I forget whether I wrote that in the theorem. So the theorem you need to add that f of a equals f of b. Okay. Anyway, so now that means this must have a derivative equal to 0 for some value between 0 and 3. So let's find it. If we take the derivative of our function, we get 2x minus 3. We want to find when the derivative equals 0, so set this equal to 0 and solve for x. So we get x is equal to 3 halves. 3 halves is a value between 0 and 3, so Rolle's theorem worked. Okay. Okay, so that's Rolle's theorem. But Rolle's theorem is actually a special case of the mean value theorem. So let's now talk about the mean value theorem. Now, Rolle's theorem has to have that extra clause that f of a equals f of b in order to use it. The mean value theorem is not going to require that the two endpoints be at the same height. They can be at different heights. Okay, so let's now state the mean value theorem. I'm just going to abbreviate that with MVT for mean value theorem. Okay, so we have to have f of x is continuous on the closed interval a to b, and f of x is differentiable, I'm just going to abbreviate that with DIF, period, on the open interval a to b. And unlike last time, f of a does not have to equal f of b. So our conclusion is going to be a little bit more complicated. F of c, the derivative of f of c, is going to equal to f of b minus f of a over b minus a for some c in the open interval a to b. Okay, so what does this mean? If we think of it graphically, this is the slope of the secant line between the points A and B. The slope of that line is that equation. You may recognize that from previous chapters. One of the very first topics we were talking about before we learned the definition of the derivative was looking at secant lines, and that's the equation of a secant line. Okay. Specifically, the secant line between x equals a and x equals b for some graph y equals f of x. Okay, but that's the slope of the secant line. Our function might go like this. Okay, so somewhere the derivative is equal to the slope of the secant line. So imagine having a line like this, shift it up until it just touches at a single point there. This is the value of c, where the slope of the tangent line to the function is equal to the slope of the secant line between the two endpoints a and b. So this is, oh, and by the way, if f of a equaled f of b, that would mean these 2 points are at the same height. This equation, the slope of the secant line would be 0. And then there'd be some point where the derivative equals 0, and that's Rolle's theorem. So Rolle's theorem is just a special case of the mean value theorem, where f of a equals f of b, therefore the numerator is 0. So the derivative equals 0. You can think of this as like Rolle's theorem. If you rotated this so that that slope is 0, then that slope would also be 0 if you just rotated the graph. Okay, anyway, so this is the mean value theorem, and let's do an example of a problem using the mean value theorem. Now, last time when I created an equation for the Rolle's theorem, I had to create it very carefully such that I knew there would be 2 points at the same height. I don't have to worry about that this time, so I can get a little bit more creative on the type of function that we can look at here. Let's see, how complicated do I want to make it? Okay, why not? Let's do like x squared plus 1 over x, okay? And let's look at between the points 1 and 2. So that's going to be my a and my b. So I want to show that the derivative is equal to the slope of the secant line for some value between 1 and 2. And let's go ahead and find it to show that mean value theorem is really working. Okay, so first of all, let me explain that mean value theorem applies. This is not a polynomial, so it's going to be a little bit more complicated. Let's just look at the derivative. That would be 2x, and then that's essentially x to the negative 1 power, so the derivative would be negative 1 times x to the negative 2, or in other words, negative 1 over x squared. Okay, notice that if you plug in any positive number between 1 and 2, this derivative is well defined. Therefore, the derivative exists. And if the derivative exists, that means that the function must have been continuous, because differentiability implies continuity. Okay, so I've really proved, and this also exists at the two endpoints, so it's continuous, the original function, even at the two endpoints. So, yeah, the original function is continuous on the closed interval, and the derivative is exists for the open interval. That's all that we needed to check. Now we're trying to find, when is this derivative equal to f of 2 minus f of 1 over 2 minus 1? That's the equation for the slope of the secant line, f of b minus f of a over b minus a. So let's calculate that. Well, if we plug in the number 2 into that, we get 4 plus a half, 4 and a half, or 9 halves, minus f of 1. 1 plus 1 is 2. The denominator is 1. 9 halves minus 2. So that's 9 halves minus 4 halves is 5 halves. So there, according to the mean value theorem, the derivative has to equal 5 halves somewhere between 1 and 2. So let's see if it does. Okay, so if we set that equal to the derivative, there should be a value of x that satisfies this equation somewhere between 1 and 2. Okay, so as it turns out, I think I made this problem a little bit too hard, because in order to solve this equation, you would have to solve a cubic equation. So I'm not going to be able to find the value exactly unless I used a graphing utility, but let me explain that this statement is still true, because I can still explain that there is a solution. I just won't be able to find the exact value of x without using a computer. Anyway, so let me prove that this statement is actually true. Okay, how can I do that? Well, let's first multiply both sides by x squared. So we get this polynomial. Let's get everything onto one side. So I'd have 2x cubed minus 5 halves x squared minus 1 equals 0. Okay, so how can I prove that this is true for some value between 1 and 2? Well, I can apply the intermediate value theorem. So this may be a problem that you might see on a homework. They might give you some function like this. They say f of x equals this. Prove that f of x equals 0 for some value between 1 and 2. Now, normally they would want you to find the exact value, but really you can just explain that it exists because if we plug in 1 into this function, so let's call this f of, well, we've already got an f of x in the problem. Let's call this g of x. Okay, what is g of 1? So if we plug in 1 in for x, we get 2 minus 5 halves minus 1. So that's 4 halves minus 5 halves is negative a half minus another 1 is negative 3 halves. Okay, next let's look at the value of g at 2. 2 cubed is 8 times 2 is 16. 2 squared is 4 times 5 halves is 10, so that's minus 10. And then minus 1, that'll be minus 11. And 16 minus 11 gives us 5. So g of 1 is a negative number, but g of 2 is a positive number. This is a polynomial, which we know is continuous. And so by the intermediate value theorem, there must be a place where it crosses any number between here and here, such as 0. Therefore, it has to cross, there has to be a value c such that g of c equals 0 for some value between 1 and 2. And g of c equaling 0 meant that, this function equals 0, which really means that the derivative equaled 5/2 for some number between 1 and 2. Okay, so you have to forgive me for making a function that we couldn't actually find the exact value, but I think this shows that there is going to be a value between 1 and 2, such that this equation equals 0, and therefore the derivative equals 5/2 somewhere. Okay, so that's going to be it for this video. Hope to see you soon. There'll be more videos coming out very soon. See you later. Bye-bye.